think that where we were was halfway through the homework set, and then we will go to the practice problem set and any questions that you have. So why don't we start out with questions? Any questions about the material that the probability, because that's really what the first exam is going to be about, probability, obviously. Or would you just like me to launch into the homework?
I have a question.
Okay.
But it kind of involves the homework, so.
Would you rather ask it in conjunction with that, or do you want to start it? Why don't you just start out with it?
Okay. There was one problem. I believe it was exponential.
Mm-hmm.
And how do we know whether to use CFD or
The CDF or PDF?
CDF or PDF?
When it is a problem that asks you for the probability of the first occurrence on, by the fifth time unit or something like that, that's exponential, or the CDF.
Okay.
And we really won't be dealing with the PDF for the exponential.
Okay.
So that's another thing. Overwhelmingly, it will be the CDF that we're using, because that's what's going to be applicable for us.
Just for the exponential
Yeah, just for the
distribution?
exponential. Yeah.
Okay.
And for actually the derivatives, the Weibull and the gamma distributions, we're going to be using the CDF for those also, and not necessarily the PDF. All right.
Is there one right word to use all the time, or they each have specific cases, or do you use all of them and then kind of compare them against each other for problems or things that you're trying to present?
I'm not sure I understand the question.
What's the right time to use each distribution?
When they're talking about
Is there one associated with each type of failure you're trying to do?
the exponential distribution is when you have one. Gamma distribution is when you have multiple components that are exponentially distributed. And the Weibull distribution is used when you have an adjustment to a single exponential component. So for instance, if I want to have adjusted for early failures or late failures, then I have an exponent to the exponent, which makes it a Weibull distribution. Does that make sense? Okay.
On the chi-squared confidence intervals, when do you know to use one-sided or two-sided?
I'm going to try to make it, try to write it in such a way that it's obvious which one I want, but usually one-sided is far more useful.
Mm-hmm.
Two-sided is kind of an academic question, whereas a one-sided one really answers what most people really want to know. So for practical applications, one-sided is usually preferable. And when I write questions, I'm going to try to make them obvious. Sometimes I'm successful, sometimes I'm not with that, but I do my best. Any other questions? Okay, well, let's...
I actually do, I'm sorry.
Okay, go ahead. No, go ahead.
I was struggling a little bit with PDFs and CDFs as well. Just really what that means. Because I was going through the homework problems primarily using the PDFs or the PMFs for the binomial and any other geometric, and I just don't know when to kind of cross over to the CDFs. And you said with the exponential and Weibull, but would we ever before those distributions?
With the discrete distributions, if I say, so for instance with the binomial, in the next 10, if I have 10 repetitions, what's the probability of exactly 4 failures? That's a PMF.
Okay.
If I say, what's the probability of at least 1 failure, which requires you to add up the probabilities for 1, 2, 3, 4, 5, all the way up to 10, if n is 10, that's a CMF, because you're accumulating more than 1.
Okay.
That's true of all the discrete. If it's just exactly, usually the term exactly means just the probability for that. That's the PMF. Yes, PMF. And if I say at least or 4 or 5, then you're adding up more than 1, and then that's a CMF.
Okay.
For the continuous, we will be overwhelmingly using the CDFs, the cumulative distribution functions,
Okay.
because we're not really interested in the probability of, because we're always interested in a range. Okay? These are continuous, so we'll be interested in the range. So CMFs or CDFs are far more applicable for our purposes. So for all the continuous, I give you the PDFs so that you know what the PDF version is, but we'll be using almost exclusively the CDFs for the continuous ones. Does that help?
Absolutely. I have another question.
Sure.
The geometric formula was based heavily on the probabilities of success. When you're dealing with probability of error or probability of failure, is moving the x-1 exponent over to the p, that's all you have to do?
Yeah, success is used very, very broadly. You can rename success, if it makes it easier, the event of interest.
Okay.
And that
So you can turn that event of interest into error.
That's right.
As long as you keep track of your P's and Q's.
That's exactly right.
Okay.
It's P's and Q's. Exactly. Yeah. So success, I think probably formally that's the way it's always phrased in textbooks. But really, what it is event of interest.
Okay.
And that could be error or anything, failure, whatever.
Great.
Any more? Anybody? Okay. Yeah, since I have a memory like a sieve, did we do A and B last week? Of 6?
Yes.
Yeah.
We did. I thought we did. Okay. Name the distribution that approximates one used in part B. What distribution is that? It approximates the binomial. Poisson. Exactly. Poisson, and they use that distribution to estimate the probability of no failures and the probability of at least 1 failure in 8 flights. Okay, so using Poisson, so let's see. Poisson is the probability of x is equal to, in this case, 0. And that is, let's see, lambda t to the x e to the minus lambda t over x factorial. Okay. So in this case, lambda, we can use the p as an approximation of lambda, so that is 0.06 times t. So t is the next 100 flights. Is, I just want to see the way the next 100 flights, right. So in the next 100 flights, to the x, which is 0, and e to the minus lambda, which is 0.06 times 100 flights, over x factorial, which is 0 factorial, and that goes to 1, that goes to 1, and we get that value right there. So the probability of 0 is 0.3 0.6, I'll say 0.61. Yeah, 0.61. Okay, and so that is the PMF, because it's exactly 0 flights, or 0 failures. Now, the next one that I asked, what's the probability of at least one failure? Now I'm adding up 1 through 8. So that's, technically, that's a CMF. But the easy way to do it is exactly right. So the probability of x equal to, or x is greater than or equal to 1 is equal to 1 minus the probability of x equals 0. And so we get about 0.39. Okay. Which you can do either by subtraction, and I think that one I did calculate by subtraction, or you can add those 8 up, which is painful if you're doing it by hand, so you always do subtraction. Yeah, I did that by subtraction, but if I were to add it out, I would get exactly the same result. And if I took it out to the same number of decimal places, it would be the same. Yeah, Bridget.
So if you asked, what's the probability of between 3 and 5 failures? You could just add 3, 4, and 5 together, and that would be the probability of 3, 4, 5.
Between 3 and 5 is 4. But greater than, you have
Or
to,
if it was, if it was
greater than or equal to 3 and less than or equal to 5, then it would be 3, 4, and 5, yes. And that would be a CMF, because it's more than one probability.
So if you ask that, it would be 2 calculations that we then have to add together.
If I asked it that way, it would be 3. Greater than or equal to 3 and less than or equal to 5. It would be 3, 4, and 5. Because greater than or equal to 3 includes 3, and less than or equal to 5 includes 5. So I'd have to add those 3.
So if we calculated the probability of greater than or equal to 3 with the CMF,
Yes.
it would be, I'm just trying to figure out, because it sounds like that would be 2 separate calculations, and then if you added them together, you'd have the probability of 3, 4, and 5.
It depends on how you do it.
Okay.
You could do greater than or equal to 3 and greater than 5 and subtract them. That would be 2 calculations, which might be easier, but probably isn't. But that would be 2 calculations that then you could subtract.
Okay.
I think the easiest and most straightforward way to do it is to just calculate 3, calculate 4, calculate 5, and then add the 3 together. You are less likely to get yourself into trouble that way, I think. C, with 95% confidence, what is the upper limit of lambda? The same level of confidence, what is the lower limit of the mean number of flights to next failure? The first one is I'm trying to imply the one side, the upper limit of lambda. And then at the same level of confidence, what is the lower limit of the mean number of flights to the next failure? That's just simply taking the reciprocal of the first answer. It's still one-sided, right? Because MTBF is just the reciprocal of lambda. Chi-squared confidence interval one-sided. And I put the two-sided one in just for, or did I ask for the two-sided one? I guess I did. Forgot. So the one-sided, we have 6 events in 100 time units, and that's the 0.06. And that makes lambda 0.06, and alpha is 0.05 because I asked for a 95% confidence interval, and then 2f plus 2 is 14. So, you go ahead and calculate 1 minus alpha at 2f plus 2 degrees of freedom, and did I get that from the table? I calculated that. But let's see, I don't know if that's on the table.
Yes.
It is on the table?
Yes.
Yeah, I just got lazy. And then our lambda is, for that, is simply the chi-squared 1 minus alpha of 2f plus 2 degrees of freedom divided by 2 times t. And that's what our lambda is. That means that lambda 95% of the time would be less than 0.1184, or just 0.12 would probably be adequate, and the converse of that would be 8.4. We would expect 95% of the time we would expect the mean time between failures to be at least 8.5 or 8.4, thereabouts. Does the interpretation of that make sense, you guys? Because that's what's important, is interpret it. I mean, you can calculate it and get the right answer, but still not know what it means, and it's important to know what it means. Is everybody comfortable with the interpretation of it? All right.
And that mean time between failure, that's considered a lower limit of that value because it's greater than 8.4?
Yes.
Okay.
Yeah. 95% of the time, I would expect it to be, the mean time between failure to be at least 8.4.
Okay.
Anybody else reasonably comfortable with that? All right. And then the two-sided of the same thing. Remember, for the lower limit, you need alpha over 2 for the lower 2f degrees of freedom, and the upper limit is 1 minus alpha over 2, or 2f plus 2 degrees of freedom. And then our lambdas, which in each case, recall for the denominator, have the same denominator times C13, which is t. It's 2 times t in the denominator for the lower limit, and 2 times t for the denominator on the upper limit. And then, so this is the lower limit of lambda, the upper limit of lambda, and then when you take the reciprocal, you reverse the inequalities. So the lower limit becomes 7.7 is our mean time between failure, and the upper limit is 45.4 mean time between failure. Like I said, you get probably answer a more interesting and important question with the one-sided than you do for the upper limit. Okay, but just to give you a comparison, that's what the two-sided confidence interval would look like. So then we are at F. The probability of the first failure will occur on the 5th flight. Once again, that's geometric, and failure in this case is the event of interest, so that becomes our success. Okay, that makes it a little bit, that's a little bit convoluted, but so whenever you see success, think event of interest. Okay, in this case, our event of interest is a failure. And so that's geometric. Fourth failure, fourth event of interest will occur on the 8th flight. That means it's Pascal or negative binomial. And the probability of the next failure will occur on the 6th flight is cumulative exponential. Because we're looking at the probability of the next failure. So let's take a look at the numbers, which are actually kind of trivial once you figure that out and keep your accounting straight. Probability is about 0.05. Out of 5 trials, the next, how did I say that? The next failure occurring on the 5th flight, and the 4th failure occurring on the 8th flight is a diminishingly small probability, which, when you think about it, really, if you have a failure that is only 6 in 100 to begin with, specifically the 4th failure occurring on the 4th flight, or the 8th flight. How did I say that? Sorry. Yeah, 4th failure occurring on the 8th flight is a very specific probability. You would expect it to be small. Now, the probability of the next failure occurring by the 6th flight for the cumulative exponential is not diminishing, it's small, nor would I expect it to be. Because my lambda, first of all, the average is 17, okay? And so that means that if I were to do the PDF, that would come to the probability of 0.5. But for the CDF, the average of 17, we get, actually, no, that does come right at about 0.5 also. So that makes, that gives us a sense of, if you can do it in Excel, obviously, you don't always have that available to you, but it gives you a sense of proportion, to know that you are getting a reasonable answer. Because if my mean is 17, that means that the probability at 17 is going to be 0.5. Now, I didn't do 0.5, but if I put 17 in there, and probability, I'm just putting something over here. Oh, yeah, that won't work out right, never mind. That means the probability of 0.5 will come at about 17. So my question, and really all you have to do with this question is plug 6 into (1 minus e to the minus lambda t), because the cumulative probability it's a t equal to 6 is 1 minus e to the minus lambda t equals 1 minus e to the minus 0.06. In this case, times our t of 6. And then we get the 0.302 gigahertz. Okay. The arithmetic of this is not difficult. What is difficult about it is identifying the right distribution, and whether to use the PDF or the CDF, or the PMF or the CDF. That's the tough part. Once you do that, the arithmetic is pretty easy. It's just applying the formula and using the right parameters. So far, so good. Okay. Okay, in the last 5,000 exposures, so in the last 5,000 exposures, the company has experienced 2 fatalities. So the probability of fatality. First of all, you get a priori probabilities, and then the next 100 exposures, and there's more than 2 options. So this is the generalized binomial, which is multinomial. That's your first clue that this is multinomial, is that you have a priori probabilities to more than 2 categories of accidents, or more than 2 categories of events. Okay, so the probability of a fatality, and I'll call it FAT, just because F is kind of a probability of failure, although fatality is kind of failure, is 2 in 1,000, or 5,000, I'm sorry. And the probability of, what's the next one? 16 major accidents is 16 out of 5,000. I call that MA. MAJ. I'm getting, in my notation, is, what was it? 16 out of 5,000. And the probability of a minor accident is 30 out of 5,000. Right? And the probability of success of none of the above is equal to 1 minus 2 plus 16 plus 30 over 5,000. Add those two together, just by subtraction, you get the 4th event of nothing occurring. So these are our a priori probabilities. Okay? Now we get to get the probability of 1 fatality, 2 major accidents, and 4 minor accidents in the next 160 exposures. So that means that we have 160 minus 1 minus 2 minus 4 is 7, so it's 153 no events. Okay, so with 153 of these, 153 of no events, there's 1 fatality, 2 major, and 4 minor in the next 160 events. So you end up with probability of 1, 2, 4, and 153 is equal to, and what we need to do is, I think it's 1 factorial, 2 factorial, 3 factorial, 153 factorial over 160 factorial, and then there's probabilities. So it's 2 to the 5,000th, whatever that is, to the first, and 16 to the 5,000th to the second, and 30 to the 5,000th to the fourth, and then 153 sorry, it's that. I'll just leave it unspecified. This guy right here to the 153rd. And you get your specific probability. A multinomial, so this is our 1, 2, 4, 153. This is the series of events for the next 160. These are our a priori probabilities. And so 1, 2, 4, 153 is each one of these to the power of this. Did I do it backwards? Yes, I think I did. Let me double check my formula.
It's 160 factorial is supposed to be on the top.
That's it. I knew that there was something backwards. Yeah, this is backwards. It's 1 factorial, 2 factorial, 4, and 3. Okay, that's the problem. And then p to the x, that's okay. Now let me look at my. That's backwards. Because it's not, it's p sub I to the x. And that's what each one of these are. It's p sub I to the x. I just wrote that backwards, so I gotta fix that. And the factorial, that's just the, I got lazy there too, and I used the factorial functions in Excel, which obviously doesn't choke on really big numbers. And that's the result then. I have to remember to fix that. When I think of it, send me an email about the multinomial labeling. Okay, other than my problem with labeling. All right, 80 respirator cartridges. Okay, then 60 for dust, 10 for mist and vapors, the rest for organic materials without replacement. Okay, I got to put without replacement there. You see without replacement, hypergeometric. That's all there is to it. And they're pretty unique too. And probability of drawing exactly 2 for dust and 4 for mists and vapors. Probability of drawing all organic materials cartridges. Okay, if I just select 9. Okay, so this is the the total, the category of interest and the number drawn, the total that exists and the number drawn, and this is the overall total and the overall number drawn, which, whereas the categories are in the numerator and the overall drawn in the denominator. This will look like probability of X1. I'll give these meaningful labels here, and then WX. Three categories. And this is the totals of the denominator. So if I have without replacement, okay, I have a total of 80. So that means that this is going to be 80 to select 9. I've got 9 respirators drawn, select 9. And so I have 80 to select 9. And in the numerator, I have 6. There's a total of 6, and I wanted to select for the best ones. Let's see, probability of 2 for dust. So for the dust ones, so this is dust, and then for the other ones, I'll call them MV, mist and vapors. And then for the final, I'll call it organic O. So, for the dust, there are 6, and I'll select exactly 3. For the organics, what did I say, 2? And for the organics, probability of 2 for dust, 4 for mists and vapors. So that means that for mists and vapors, I have a total of 10. I want to select 4. And then that means that there's 3 left. And the remaining 80, that's 64. And I want to select 3 of those. I think I got that right. A little bit of counting there. And that specific probability is small, as you might imagine. But when we're doing the probability of selecting only organic materials, that's a somewhat higher probability because there's 64 out of 80. And use the same formula except 0 for dust, 0 for mist and vapors, all 9 of them being organic materials. And these are the combinations for each of them, and I want to do the arithmetic on it. And that's the probability about 0.12. About 12% likelihood of drawing that, all of them. And once again, these kind of, the hypergeometrics kind of jump out at you. So those aren't nearly as difficult to determine the right distribution. Okay?
I have a question on that.
Sure.
Maybe above and beyond, but could you figure out if you're the probability of grabbing the one you need? Say you need a dust mask 50% of the time and mist and vapor 20% of the time, and so on and so forth.
What you'd have to do is, on one with replacement on one draw, getting the probability of the one that you need. Okay. So, if I need, you'd make the overall number 1, the other zeros, and the one dust, one mist and vapor, exactly one organic material. Okay. So, then you have the probability of drawing each one of those individually on the first draw. Then, if we'd have to do another step with the 20% of the time, and the other step would be, I have to think about that a little bit. It is somewhat, it's a little bit beyond our purview, but it's still an interesting question. Let me think about it, that one. But for each one of the individual, it's just the probability of drawing it and no other on one draw. But then doing that next step, that may have a probability associated with it. Let me think about it a bit. Process observed for 1,000 hours and 36 human operator errors are recorded. Okay, so it looks like we have a Poisson process, probably. Okay. Probability of exactly 3 errors occurring in the next 50 hours of operation. Probability of at least 1 error occurring in the next 50 hours of operation. Name the distribution. It would be a Poisson. Probability of the next error failure occurring by the 20th hour is cumulative exponential. And then a one-sided and a two-sided for lambda. So this is a Poisson process, and wherever you have a Poisson process, you have either the Poisson distribution or the exponential, the cumulative exponential in this case. Okay. So the numbers then for Poisson, this is what our lambda looks like from 36,000 hours. And remember that, I probably should have made it more obvious, that lambda, p has to be between 0 and 1, it's probability. It has to be between 0 and 1. Lambda, however, does not have that constraint. Lambda can be any number. And that's why Poisson can only be an approximation of the binomial. So I can get a lambda of 500, possibly, and that makes sense, because it's not a probability. It's an average event per unit time for a Poisson process. That's different. This happens to be 36 errors in 1,000 hours, which happens to be less than, between 0 and 1. But, so if I operate for 50 hours, that's my t, that's my 0.036, that's my lambda t. Exactly 3 errors is just, that's the CMF, the cumulative mass function. It's a single event. The probability of at least 1 error in the next 50 hours of operation is 1 minus the probability of 0 errors. With Poisson, because it goes on to infinity, theoretically, we have to do it by subtraction. You can't add all of them up and come up with the probability of at least 1 error. Now this is a CMF, but we can only do it by subtraction in this case. Otherwise we're only approximating it, because we can only go out to, say, 100 hours, in which case we get diminishing and small results, and we'll get an approximation, but it's not a true approximation. But it's not the true answer, I should say. It's a good approximation, but not the true answer, I should say.
So when you do your 1 minus, you're doing your 1 minus of 1 event, as opposed to your answer for 3 events or 3 errors. Or can you do the 1 minus 3 errors?
I could say 3, at least 3.
At least 3.
Yeah,
okay.
and then I would have to add up 0, 1, and 2 and subtract that from 1.
Right.
So far, so good? And then the exponential, again, this goes to infinity also. Remember the cumulative, the continuous functions go to infinity, as does the Poisson, but the other discrete functions don't go to infinity. It's just the Poisson that does. So probability of at least 1 error occurring by the 20th hour, okay, or the first error occurring by the 20th hour, in either case is the same. It is 0.51, because we just calculate 1 minus e to the minus lambda t for t equal to 20. The confidence interval is one-sided and two-sided for that lambda. 95% of the time, we would expect 21 or more hours to have occurred between errors, and errors will occur between 20 and 39.7, 95% of the time. Slightly different phraseology, different questions answered. The next one, customers arrive at the shop at the rate of 30 per hour. What is the probability that 2 customers will arrive in 5 or fewer minutes? First thing to pay attention to is that this is given in per hour, and I asked for the question in terms of minutes. So if 30 arrive per hour, that means it's 30 for 60 minutes. And per 1 minute, it would be 0.5 per minute. Okay, 30 and 60 minutes is is 1 for every 2 minutes, or a half customer on the average per minute. Okay, so it's 0.5 per minute. Okay, so you convert that to minutes, and then you have 2 customers, and each of them have this lambda, so that's 2 different exponential distributions. And that makes it gamma. For it being less than or equal to 5, we have to take 1 minus that formula. And in this case, r equals 2 because we have 2 customers. And x equals 5 because it's 5 minutes. And lambda is 0.5 per minute. And at that point, it's a plug and chug, but I'll write that out just to make it a little bit clearer. It's f of x less than or equal to 5 equals 1 minus, and the first term of this is for k equal to 0, and for k equal to 0 is lambda k, well, I'll just write it out, lambda x 0, and e to the minus lambda x over k factorial, which in this case is 0 factorial. And that would be plus lambda x the first times e to the minus lambda x, and over 1 factorial. Okay. So that goes to 1, that goes to 1, and our lambda and our x are 0.5 and 5. And this is just lambda x, and that's 1. So we get 1 minus e to the minus lambda x. And you can simplify this more, but you can also just do it this way. It's easier to keep track of. And where lambda is 0.5 and x is 5. And given that, that's the probability. And again, if you look at the question, if we have 1 customer arriving every 2 minutes, the probability that 2 customers will arrive in the next 5 minutes is pretty good odds. It makes sense that it would be on the order of 0.7. I believe that answer. So this is a way to, what you have to think about is if it looks like an exponential and there's more than 1 of them occurring, then you go to gamma, because gamma is multiple exponentials. This one is kind of a plug and chug. I wasn't very imaginative when I came up with it. But we have the MTBF, and we have the shape parameter, and then we have the time, and the Weibull distribution. Alpha is a shape parameter, beta is the MTBF, and x is 50. That's our. It's really just the It's really just the exponential with an exponent on the exponent. Right? This little alpha up here. Because if alpha is 1, that becomes just the cumulative exponential distribution. Okay? And if it's at least 50 hours, then x is less than or equal to 50, and that's our probability. So it's just a little bit of an exercise in the libel and what each of the parameters are supposed to mean. Questions on any of these? Okay. Well, why don't you take 10 minutes, and at about 4 o'clock, then we'll go over the practice problem set. And also, what I would like to do, I intended to do this earlier, but it's still early this semester, is to talk about your projects. What I'm going to do is assign everybody a hazard analysis technique. That seems to work best. And then that's what you'll learn and teach to the class in a 30 or 40-minute presentation at the end of the semester when we do that. But what I'm going to do is, I have a list of them and just randomly assign them to you guys. And you can go off and do that whenever you feel like it. And I'll do it before the end of the semester, that is. So anyway, take 10, and I'll do that in the break. We can go over the practice problems.